Hello guys, welcome back to our channel. In this video, we will solve a problem from chapter 6, which is the vapor power cycle, gas power cycle, and diesel power cycle. So here we have a problem. A steam power plant operates of an ideal Rankine cycle with two stages of reheat and has a net power output of 120 megawatts. So steam enters all three stages of turbine at 500 degrees Celsius. The maximum pressure in the cycle is 15 megapascal and the minimum pressure is 5 kilopascal. The steam is reheated at 5 megapascal the first time and at 1 megapascal the second time. Show the cycle on a TS diagram with respect to saturation lines. And determine A, the thermal efficiency of the cycle, and B, the mass flow rate of steam. So in this problem, a steam power plant operating on an ideal Rankine cycle with two stages of reheat is considered, and the thermal efficiency of the cycle and the mass flow rate of the steam are to be determined. Also, we are tasked to draw or to show the cycle on ATS diagram with respect to saturation lines. So here we analyze, our analysis is that these values can be seen from steam tables and our steam property table, and this can be found in tables A-4, A-5, and A-6. So this is our TS diagram, and here from our steam property table, we have the enthalpy for the saturated liquid at 5 kilopascal. We have 137.75 kilojoule per kilogram, and our specific volume for saturated liquid at 5 kilopascal is equal to 0.001005 cubic meter per kilogram. This can be seen in table 5. And for our network input, we have the specific volume multiplied by the difference between pressure at the final pressure and the initial pressure. So we have 0.001005 cubic meter per kilogram multiplied by the quantity of 15,000 minus 5 kilopascal. So this 15,000 here is from our given, which is 15 megapascal, and we multiplied it into 1,000 kilopascal over 1 megapascal so that we can convert this megapascal to kilopascal. So we have 15,000 kilopascal minus 5 kilopascal multiplied by 1 kilojoule all over by 1 kilopascal per cubic meter. And solving this equation, we get 15.07 kilojoule per kilogram. Next, for our final enthalpy, we have initial enthalpy plus the work input equal to 137.75 plus 15.07. That is equal to 152.82 kilojoule per kilogram. And for our pressure at state 3, we have 15 megapascal, and our temperature is 500 degrees Celsius. So the enthalpy for 15 megapascal is equal to 3,310.8 kilojoule per kilogram, and the entropy for 500 degrees Celsius is equal to 6.3480 kilojoule per kilogram per Kelvin. And this can be seen in our steam table A-6. So for our pressure at state 4, since as you can see in our TS diagram, from 1, 2, 3, 4, state 4, we have 5 megapascal, and our entropy at state 4 is equal to our entropy at state 3. So we have our enthalpy at state 4, we have 3,007.4 kilojoule per kilogram. So for our state 5, 6, 7, 8, we have at state 5, we have our enthalpy equal to 3,434.7 kilojoule per kilogram, and our entropy is equal to 6.9781 kilojoule per kilogram per Kelvin. And at state 6, we have at 1 megapascal, we have our enthalpy equal to 2,971.3 kilojoule per kilogram. And for our at state 7, from the pressure 1 megapascal and 500 degrees Celsius, our enthalpy is equal to 3,479.1 kilojoule per kilogram, and our entropy is equal to 7.7642 kilojoule per kilogram per Kelvin. And at state 8, at 5 kilopascal, and that is equal to 0.9204, and our enthalpy is equal to 2,367.9 kilojoule per kilogram. Then now we can solve for the Q in, and that is equal to the difference between the enthalpy at state 3 minus the enthalpy at state 2 plus the difference between the enthalpy at state 5 and state 4 plus the difference between the enthalpy at state 7 and state 6. So plugging in the values, we have 3,310.8 minus 152.82 plus 3,434.7 minus 3,007.4 plus 3,479.1 minus 2,971.3, we get 4,093.1 kilojoule per kilogram. Next, we can solve for the Q out, which is equal to the saturated vapor of the enthalpy minus the initial enthalpy. So that is equal to 2,367.9 minus 137.75. We get 2,230.2 kilojoule per kilogram. And now we can solve for the network, that is equal to Q in minus Q out, and we have 4,093.1 minus 2,230.2, and we get our work net 1,862.9 kilojoule per kilogram. So now, since we have the value for our Q in, Q out, and our work network, we can now solve for the thermal efficiency of the cycle. And that is denoted by this formula. We have the thermal efficiency is equal to the network over Q in. So we have 1,862.9 kilojoule per kilogram all over by 4,093.1 kilojoule per kilogram. This units will be cancelled, and we have 45.5%. So our thermal efficiency in this problem is 45.5%. Next, since we have already get the thermal efficiency, we can solve for the mass flow rate of the steam, and that equal to the mass flow rate is equal to the rate of network all over by network. So we have 120,000 kilojoules per second all over by 180, or 1,862.9 kilojoule per kilogram. That is equal to 64.4 kilogram per second. So this is our answer. I hope you understand this video, and thank you for watching.